Welcome to Budget Power Electrical Solutions. In this series, we will refresh useful electrical formulas from basic to advanced for electrician exams, trade license exams, and real practical electrical work. We'll test your memory, explain each formula clearly, and use simple practical examples. So, let's see how much you remember. Let's begin with question number 1. For this simple resistor circuit, what formula relates voltage, current, and resistance? Think about the relationship between V, I, and R. The answer is Ohm's law. The basic relationship is V equals I times R. Here, V is voltage, I is current, and R is resistance. From the same formula, current can be written as I equals V divided by R, and resistance as R equals V divided by I. For a linear resistor, the resistance remains constant. Now that we remember the formula, let's see how we actually use Ohm's law in a real circuit calculation. Now let's apply Ohm's law to this simple circuit. We have 24 volts and 12 ohms. Using I equals V divided by R, 24 divided by 12 gives us 2 amperes. But here is something important to remember. When using Ohm's law, always pay attention to whether the resistance is given in ohms or kilo ohms, because that affects the unit of the current answer. Let's look at that more clearly in the next slide. Now the voltage is still 24 volts, but the resistance is 2 kilo ohms. Using the same formula, 24 divided by 2 kilo ohms gives 12 milliamperes. So remember this useful relationship. Volts divided by ohms gives amperes, while volts divided by kilo ohms gives milliamperes. Keeping the units consistent helps you avoid a very common calculation mistake. Now let's move to question number 2. Where can Ohm's law be applied? Can we use it in DC circuits, single-phase AC circuits, and three-phase AC circuits? The answer is all three. Ohm's law can be used in DC, single-phase AC, and three-phase AC circuits. For DC and purely resistive AC loads, we use V equals I times R. For general AC circuits, impedance becomes important, so we use V equals I times Z. Now let's see how this works in practical examples. First, let's look at a DC motor. Here we have a 24-volt DC motor with an armature resistance of 6 ohms. At starting, back EMF is almost zero, so using Ohm's law, I equals 24 divided by 6, which gives 4 amperes. As the motor starts rotating, back EMF develops and reduces the current. Now let's see the same principle in a single-phase AC circuit. Here we have a 120-volt single-phase AC supply connected to a purely resistive heater of 30 ohms. Because this is a resistive load, we can use Ohm's law with RMS values. I equals 120 divided by 30, which gives 4 amperes RMS. This shows that Ohm's law also works directly with a purely resistive single-phase AC load. Now let's move to a three-phase example. Here we have a balanced three-phase star-connected resistive heater. The line voltage is 400 volts, so first we find the phase voltage. 400 divided by square root of 3 gives approximately 231 volts. Each phase has a resistance of 20 ohms, so 231 divided by 20 gives about 11.55 amperes per phase. In a star connection, line current equals phase current, so the line current is also about 11.55 amperes. So the key point is, in a three-phase circuit, we apply Ohm's law per phase, then use the correct line-to-phase relationship. Don't worry if some of these relationships are not familiar yet. As we continue this series, we'll go step by step from basic to advanced and see exactly where each formula is used. Now let's move to question number 3. If the voltage stays constant and the resistance increases, what happens to the current? Think about the relationship between V, I, and R. The answer is current decreases. From Ohm's law, I equals V divided by R. So when voltage stays constant, increasing resistance makes it harder for current to flow. That means more resistance, less current. Now let's prove it with a simple example. Here the voltage stays at 24 volts. With 12 ohms, the current is 2 amperes. When the resistance increases to 24 ohms, the current drops to 1 ampere. So this clearly shows the inverse relationship. As resistance increases, current decreases. This is a useful idea for basic circuit calculations and troubleshooting. Now let's move to question number 4. If you know the voltage and current of a load, how do you calculate the electrical power? Think about the relationship between voltage, current, and power. The answer is the basic power formula. P equals V times I. Here, P is power in watts, V is voltage in volts, and I is current in amperes. This formula works directly for DC circuits and for purely resistive AC loads. Now let's use it in a simple practical example. Here we have a 120-volt resistive heater drawing 4 amperes. Using the power formula, P equals V times I. So, 120 times 4 equals 480 watts. That means this heater is using 480 watts of electrical power. This is a common calculation used for load estimation, appliance power checks, and basic electrical troubleshooting. Then we can naturally move on with. Now that we know the basic power formula, let's see how power can also be calculated when resistance is known. Now let's move to question number 5. If voltage is not given, but current and resistance are known, how can we calculate electrical power? Think about which formula we can use. The answer is P equals I squared R. We get this from 2 formulas. First, P equals V times I. And from Ohm's law, V equals I times R. So if we substitute IR in place of V, we get P equals I times R times I. So finally, P equals I squared R. We use this formula when current and resistance are known. Now let's use the formula in a practical example. Here, the current is 5 amperes and the resistance is 8 ohms. Using P equals I squared R, P equals 5 squared times 8. That becomes P is equal to 25 times 8. So the result is P equals 200 watts. This type of calculation is useful for heating elements, ovens, toasters, and other resistive loads. Short transition. Now that we know P equals I squared R, next we can look at power when voltage and resistance are known. Now let's move to question number 6. If current is not given, but voltage and resistance are known, how can we calculate the electrical power? Think about how we can combine the power formula with Ohm's law. The answer is P equals V squared divided by R. We start with the basic power formula. P equals V times I. From Ohm's law, I equals V divided by R. So we substitute V divided by R in place of current. That gives P equals V times V divided by R, or simply, P equals V squared divided by R. We use this when voltage and resistance are known. Now let's use the formula with a resistive heater. The supply voltage is 120 volts RMS, and the heater resistance is 30 ohms. Using P equals V squared divided by R, we get 120 squared divided by 30. That is 14,400 divided by 30, which gives 480 watts. So this heater consumes 480 watts of electrical power. For a purely resistive AC load, remember to use the RMS voltage value. Then we can connect naturally. Now we have seen all 3 basic power formulas. Next, let's look at electrical energy and how power relates to time. Now let's move to question number 7. If you know the power of a load and how long it operates, how do you calculate the electrical energy used? Think about how power and time are related. The answer is E equals P times T. Here, E is electrical energy, P is power, and T is time. If power is in watts and time is in hours, the answer is in watt-hours. For larger values, we normally use kilowatt-hours, where 1 kilowatt-hour equals 1,000 watt-hours. Now let's apply this to a practical example. Here we have an electric heater rated at 2 kilowatts, running for 3 hours. Using E equals P times T, we get 2 kilowatts times 3 hours equals 6 kilowatt-hours. So the heater uses 6 kilowatt-hours of electrical energy. This is the same type of energy unit we commonly see on an electricity bill. Now let's move to question number 8. For a single-phase AC load, is electrical power always simply P equals V times I? Think about what changes when the load is not purely resistive. Slide 2, answer. The answer is not always. For a purely resistive load, voltage and current are in phase, so P equals V times I. But for inductive or capacitive loads, we must include power factor. P equals V times I times PF. And V times I alone gives us the apparent power, measured in volt-amperes. Now let's see this with a practical motor example. Here we have a single-phase AC motor supplied with 230 volts, drawing 8 amperes, with a power factor of 0.80. First, the apparent power is 230 times 8 equals 1840 volt-amperes. For real power, we include the power factor. 230 times 8 times 0.80 equals 1,472 watts, or approximately 1.47 kilowatts. So this example shows why P equals V times I is not always the real power in an AC circuit. Now let's move to question number 9. For a balanced three-phase AC load, what formula do we use to calculate real power? Think about which values are needed in a three-phase system. The answer is P equals root 3 times line voltage times line current times power factor. So, P equals square root 3 times VL times IL times PF. Here, P is real power in watts, VL is line voltage, Illinois is line current, and PF is power factor. This formula is used for balanced three-phase loads. Now let's use it in a practical example. Here we have a balanced three-phase motor load. The line voltage is 400 volts, the line current is 10 amperes, and the power factor is 0.85. Using the formula, P equals square root 3 times VL times IL times PF. We get P is equal to 1.732 times 400 times 10 times 0.85. So the result is about 5,889 watts, or approximately 5.89 kilowatts. This is very useful for three-phase motor load estimation and troubleshooting. Short transition. Now we have covered single-phase and three-phase power. Next, we can move into another important practical formula. Now let's move to question number 10. In a balanced three-phase star or Y connection, what is the relationship between line voltage and phase voltage? This is a very important three-phase formula, so let's see the answer clearly. In a star or Y connection, the line voltage is equal to root 3 times the phase voltage. So, VL equals square root 3 times phase. And if we want to find phase voltage, we rearrange it as VL phase equals VL divided by square root 3. So the key point to remember is, in star connection, line voltage is higher than phase voltage. Now let's use a practical example. Here we have a balanced three-phase star system with a line voltage of 400 volts. We want to find the phase voltage. Using the formula, V phase equals V line divided by square root 3. So, V phase equals 400 divided by 1.732. That gives approximately 231 volts. So the result is, phase voltage is about 231 volts. That means in a 400-volt three-phase star system, each phase winding sees about 231 volts. Short transition. Now that we understand the star connection, next we can look at the delta connection and see how line voltage and phase voltage relate there. Now let's move to question number 11. In a balanced three-phase delta connection, what is the relationship between line voltage and phase voltage? We already saw the star connection, so now let's compare it with delta. In a delta connection, the line voltage is equal to the phase voltage. So, VL equals VP, and that also means V phase equals V line. The reason is simple. In delta, each phase is connected directly across two lines. So the key point to remember is, in delta connection, there is no root 3 difference for voltage. Now let's use a practical example. Here we have a balanced three-phase delta system with a line voltage of 400 volts. We want to find the phase voltage. Since in delta, phase equals V line, the phase voltage is simply 400 volts. So the result is, phase voltage equals 400 volts. That means in a 400-volt delta connection, each phase winding sees the full 400 volts. Short transition. So now we can clearly see the difference. In star, phase voltage is lower than line voltage. In delta, phase voltage is equal to line voltage. Next, we can move to the relationship between line current and phase current. Now let's look at another important three-phase relationship. In a balanced star or Y connection, what is the relationship between line current and phase current? We already saw that star voltage uses the root 3 relationship, but what happens with current? In a star connection, the answer is simple. Line current equals phase current. So, I line equals I phase. Each line conductor is connected in series with one phase winding, so the same current flows through the line and the phase. A good memory tip is, now let's use a practical motor example. This balanced three-phase star-connected motor has a phase current of 10 amperes. Because in star, I line equals I phase, the line current is also 10 amperes. So each line L1, L2, and L3 carries 10 amperes in this balanced system. This relationship is very useful for motor current calculations and three-phase troubleshooting. Now we know the current relationship in star. Next, let's compare it with delta, where the √3 relationship moves to the current side. Now let's move to the delta current relationship. In a balanced three-phase delta connection, what is the relationship between line current and phase current? We already learned that in delta, line voltage equals phase voltage. Now let's see what happens to the current. In a delta connection, the line current is equal to √3 times the phase current. So, I line equals square root 3 times I phase. And if we want to find phase current, we can rearrange it as I phase equals I line divided by square root 3. So the key point to remember is, in delta, voltage is the same, but current has √3. This happens because each line current is the vector sum of two phase currents. Now let's use a practical example. Here we have a balanced three-phase delta-connected motor load. The phase current is 10 amperes, and we want to find the line current. Using the formula, I line equals square root 3 times I phase. So, I line is equal to 1.732 times 10. That gives 17.32 amperes. So the result is, line current equals 17.32 amperes. This is very useful in delta-connected motor current calculation, load analysis, and troubleshooting. Now that we understand the formula, let's look at one final example that connects industrial practical work with trade and license exam knowledge. We'll use a real star-delta motor starting situation to see how these voltage and current relationships are applied in the field, and how the same concept can appear in an electrical exam question. Now let's look at one final example that connects industrial practical work with trade and license exam knowledge. In a real star-delta motor starter, why does the motor start in star and then change to delta? This is a very common practical and exam-related question, so let's understand it clearly. The answer is simple. The motor starts in star to reduce the voltage across each winding. Because the phase voltage is lower in star connection, the starting current is reduced, and the starting torque is also reduced. After the motor gains speed, the starter changes to delta. In delta connection, each winding receives the full line voltage, so the motor can run at normal full load condition. So the key idea is, start in star for lower starting current, then run in delta for full voltage and normal operation. Now let's take a practical and exam-related example. Suppose we have a 400-volt supply and a motor designed for 400-volt delta and 690-volt star. When the motor starts in star, each winding gets 400 divided by √3, which is about 231 volts. So the winding voltage is lower, and that helps reduce the starting current. After starting, the motor changes to delta, and now each winding gets the full 400 volts. That's the practical reason behind star-delta starting, and it's also a very common trade and license exam concept. If this series is helping you refresh and remember electrical formulas, subscribe to Budget Power Electrical Solutions, click the bell icon, and leave a comment. Thank you for watching, and I'll see you in the next episode.